Hey, I was just thinking I would give you a little bit more help on some of these problems on definite integrals packet page 3 as you're estimating area between a curve and the x-axis using rectangles to help you estimate. We were caught on page 3 in the middle of number 3, and I just want to make sure we see this problem through the whole way. So you have a picture already with these 4 rectangles we're going to use as an estimate, and their left endpoints all land on part of this f of x curve, this hyperbola branch here. And we said the width of each rectangle was 0.25. And then do you remember how we got all the heights? I split up the interval from 1 to 2 into a quarter, right? 1, 1 1/4, 1 1/2, 1 3/4. And then we go back up to the function to get the height of the rectangle. So 1 over 1, 1 over 1.25 gives you 8/10 or 0.8. 1 over 1.5, we could just put 2/3 there, right? It's 1 over 3/2. And then 1 over 1.75 is going to be rounded 0.57. This is all just an estimate, 1429. Okay, let the calculator help you there. Feel free to get that in. We're going to round this one, 0.7595 square units. Just make sure you look back up at the picture and just make sure that looks like it makes sense. It wouldn't quite be a full unit of area, and we also know this is an overestimation. You're going to try these last 3 on your own. I did want to give you a head start with the picture too, so this is just some help on that. Think of y equals x squared. Feel free to use all the space that's given to you here, right? If do I have enough room? Let me just, I'll just make it a little smaller here. I'll go 1, 2, 3, 4. You have 0 squared is 0, 1 squared is 1, and 2 squared's up at 4. And you have the other side of that, but we really just care, whoops, not my nicest looking parabola, but you really just care about the part between 1 and 2. So from x equals 1 to x equals 2, we want this shaded area, not that I'm shading it, but between the x-axis and the curve. So from 1 to 2, you're going to go with 4 rectangles. I'm going to have to squeeze these guys in. So their left-hand endpoints hit the curve. So 1, we'll say the second one, whoops, left-hand endpoint here, 2, and then 3, and then 4. I'm hoping your picture looks a lot better than mine does. That's not very pretty. This is going to be an underestimation. You're going to set up the area as the integral from 1 to 2 of f of x squared, taken with respect to x. Since your interval, this is the same as the last one. It's 1 unit long, the whole interval, and you're splitting it up into 4 parts. So the width of each rectangle is a quarter. And then you want left endpoints, f of 1, I'll just put plus, you can fill in the rest of them. They're the same numbers that we used in number 3. So you're going to finish up 4. 5, I think you've got. You're good at graphing a y equals square root of x. I'll just help you on the picture. So for 5, 0, square rooted is 0. If I square root 1, I get 1 back. And the next perfect square that's convenient to square root would be the whole number 4. So you get that French fry graph. And you want all the way from 0 to 4 rectangles to approximate this. Look how the first one has no height. If it's left-hand endpoints, you're just having a rectangle that starts left-hand endpoint at 0, another one at 1, another one at 2, and the last one at 3. So these 4 rectangles, set it up. This one has a width, so area is the integral from 0 to 4 of f of x, taken with respect to x. And this time you have an easy width of the rectangles, 1, 2, 3, 4. They look like they're each 1 unit wide. Do f of, start with the left-hand endpoint, f of 0, f of 1, f of 2. You can go back to the function to get these values, f of 3. And that should give you your underestimation. Go ahead and find those, plug in, and solve for 5. And then the last one, 6, I definitely wanted to help you with this graph because you have another rational function. It's just been a little while since we found features of that. So I'm going to leave it up to you to finish 4 and 5. For 6, we go picture first. Tell me some features. Do you know the x-intercept of this graph? Well, you could set the whole function equal to 0, meaning you want the top to be 0, and you have a dot right at 0. You can confirm that by finding the y-intercept, plugging in zeros for the x's, and you get 0 over 1. What were other things we always looked for? With rational functions, like a couple problems ago, we looked for asymptotes. This one has a VA, right? Wherever the denominator would be 0, x equals -1. So you've got this graph here. And a VA there. Does it have an HA? Is it top heavy, bottom heavy, or balanced? Looks like you have x to the first on top and bottom. We're balanced. Ratio of the leading coefficients is going to be 1 over 1. So you have this asymptote here. Okay. So that's what we know so far. Because I see this point here, if I plugged in some more points or if I checked on a calculator, I'd get two hyperbola branches. One that I don't care about too much and another one that I really do care about, the one that's between 0 and 4. So I'm just going to draw this branch as best I can to make it look like it's approaching the asymptotes. And then look how your rectangles would look here. Let's see. You're going 4 left-hand endpoints. So one starts at 0. Then, whoops, the next one, try that again. The next one starts at 1. And I think this would be an underestimate. Hopefully this is going better for you because I'm shifting stuff around. Okay, take 2. Next rectangle, carefully. Next rectangle, left-hand endpoint. And then the last one, like that. The picture is not as important as your calculation for the estimation. So let's try it. You want the area from 0 to 4. 0 to 4, right? That's what the interval says, of the function x over x plus 1. So we could write it in this definite integral notation since we have the numbers on top and bottom. Think of the width of each rectangle. I think we just use 1 again, like in the last problem, right? Width is going to be 1. And then the height of each rectangle. These are left-hand endpoints, f of 1, f of 2, f of 3, and f of 4. So if the picture, I mean, you saw how sloppy my picture was for number 4. I'm embarrassed that it even looks like that. The picture is secondary to this calculation, this estimation that you're giving me using the sum of areas of rectangles. Hope things are going well, and I will catch you next time.